From an observational perspective, one of the things we can measure is what we call the star formation rate function. You have an example right here, and this is essentially telling you the amount or the number density of galaxies for a given volume as a function of how many stars they're forming. What we can then do is if we determine this for different redshifts or different look-back times, we can see how galaxies as a whole are evolving, whether they're forming more stars in the past or less stars in the past. For now, let's focus on trying to determine and understand this function for the last 11 billion years. The way we do this is essentially imagining that we take this volume and that we go back in time with a time machine, and then we just count how many galaxies would be in this volume for each unit of star formation rate. Now, because we want to make comparable measurements, this volume will actually take into account the expansion of the universe, and is called a co-moving volume. So because we know how much the scale of the universe has changed with time, we are changing this cube to take that into account, so that the result is not just driven by the fact that the universe is expanding. Once we do those measurements, then the typical way to model them and actually understand their evolution is to fit them with the Schechter function that we covered in section 13. And one of the big advantages of using a Schechter function is that the integral provides you an analytical solution that is given by the typical number density of star-forming galaxies times their typical star formation rate times the gamma function of alpha plus 2, which you can look at a table or, for example, online. Now, by determining the star formation rate function for different redshifts, what we've been able to find is that at redshift 0, so this is the local universe, this is where the typical star formation rate of a galaxy is. It's about something like 3 to 5 solar masses per year. And remember that as a Schechter function, this is a power law. This is essentially described with the power of alpha. And then there's the exponential decline over here. What we find is essentially if we go back in time, the star formation rate function looks very similar in terms of shape, but it actually shifts towards the right. Therefore, the typical number density of star-forming galaxies is not evolving that much, actually goes up a little bit, but the strongest evolution that we see is the typical star formation rate of galaxies is going up over the last 11 billion years if we move to the past. We can even quantify this change of the typical star formation rate, or the knee of the star formation rate function, essentially how much this evolves if we go back, or if we go forward in time, how it evolves from essentially here, it's almost 100, more like 80 solar masses per year, all the way down to something like 5 solar masses per year. And if you plot that, you can produce a plot like this, and you can show that actually the decline of the typical star formation rate of a galaxy is pretty much exponential. Even more importantly, this exponential decline seems to hold regardless of the kind of galaxy. We've seen in section 12 that we can also classify galaxies in terms of their mass. So what we're seeing is that no matter whether you're a dwarf galaxy or a more sort of normal or very big galaxy, then you're always experiencing this decline. And the big difference is if you're a dwarf galaxy, you're already forming way less stars, but you're still going to form even less if you sustain it. While if you were a more massive galaxy, you would be likely forming a lot of stars. And if you're a massive galaxy later on, then the typical star formation rate will be much lower. An important question that we therefore need to address is, what does that all mean for how galaxies essentially evolve? What this implies is that regardless of whether you're a small galaxy or a big galaxy, even if you manage to continue to form stars and you don't die, and we'll see that galaxies can actually quench or stop forming stars, then there must be different physical processes, or perhaps the same physical process but acting different ways, to essentially lead to 3 different main outcomes. On one hand, we'll see that some processes can lead to galaxies getting quenched or really stopping forming stars. There are processes that actually are able to keep them quenched so that galaxies don't come back to life. And also processes, to explain what we've just seen, to reduce their star formation rates, even if they continue to be active. Now, if we use our knowledge of the star formation rate function and we actually integrate that Schechter function for each time, what we can do is produce something like this. We can actually determine what is the star formation rate density as a function of time. In this case, you can even have a look at the tons of stars produced per cubic light year per minute. So you can think that that co-moving volume had a side of essentially 1 light year. And what these results allow you to do is essentially model this decline. This is a factor of 30 from 11 billion years ago until today. Now, if you try to fit it in log space, perhaps the simplest model is something like this. And this allows you to have an idea of how the star formation rate density, essentially the amount of star formation that is happening per co-moving volume in the universe as a function of time, is declining with this functional form. Over the last 20, 30 years, lots of people throughout the world have tried to do these experiments and measurements. And this is the reason why the community as a whole now has amazing measurements like these. And all the observations point essentially towards a peak that happened about 11 billion years ago. This is a redshift of about 2 to 2.5. So there was definitely a steep rise from the early universe all the way up to that redshift. But then since then, over the last 11 billion years, the star formation rate density of the universe has been declining. There's, of course, a lot of scatter, and you can see there's huge differences for a fixed redshift or time. This is mostly to do with people using different measurements that have different sensitivities and also different biases. So it is really important to try to get the best possible methods and also to do it in a self-consistent way. And this is one of the last studies to actually do it in a self-consistent way all the way to the very early universe to show this peak around 11 billion years ago.